Hello, I'm Ben Glasspool, and I'm the head of emerging chemical synthesis at Merck, or MilliporeSigma, here in the US and Canada. Welcome to our first ever virtual seminar. I'd like to spend a few minutes with you talking about what's new and innovative in our early discovery, synthetic chemistry, and medicinal chemistry spaces. A large portion of the innovation and new products that we bring in stem from academic collaboration. And in fact, we've introduced over 1,000 products coming from these collaborations in the last few years. The chemistry of the collaborating academics is found in our professor portals, as well as the products that we've commercialized in conjunction with them. And so this is a role that we take pretty seriously, and we think is perhaps unheralded because through our global supply chain and with our website that gets viewed by millions of chemists every year, we believe that we're able to take academic invention, academic innovation from JAX ASAPs and from Angewandte Early View and turn it into actual tangible chemical reagents that a chemist who's reading those articles can apply wherever they are in the world to their chemistry and to their research. And through this academic network and in trying to stay current and tapped in, an added benefit is that we're able to support academic research through sponsorships, lectureships, and so on. And so the question is how to focus that network. What types of reagents should we commercialize? And the answer is a lot of different types of reagents, but with focus around those which are most relevant to drug discovery. And so where those reagents used to, in previous decades, focus around building blocks, reagents, and catalysts, so white powders that you would find in amber bottles, we've tried to expand that remit to include all chemical synthesis technology that might be applied towards drug discovery, spanning from biology all the way to preclinical. So that's what I would like to talk a little bit about today. And so I've broken this into 4 quick sections along this drug discovery workflow. And so typically this is a longer conversation, and be happy to have that with you if you'd like. But for today, and at least for this virtual seminar, looking at 4 pieces. First, looking at what to make. And so looking at tools for lead discovery. And then once we figured out what to make, well, the question arises, how should we make it? And so a quick conversation about our retrosynthetic software tool called Cynthia. Once we figured out how to make it, then we have to actually go about the hard process of making it. And so some new medicinal chemistry tools and reagents, and some platforms that allow us to do those syntheses more effectively. And then lastly, and a new area for us is in chemical biology. And so once we've made those small molecules, can we use chemical biology tools to make those small molecules useful in other ways, in other biological processes? So first in lead discovery, and so this isn't a traditional area for us for sure, but we realized that with the advent of DNA encoded libraries, there's some, we could bring some value into this space. And so for those of you that aren't completely familiar with DNA encoded libraries, just a quick summary here. And so where a traditional lead discovery screen would be done through high throughput screening with millions of compounds of a curated library with robotics, a DNA encoded library allows that an entire multi-million, multi-billion compound library to be screened all at once. So that library exists within, in this instance, within one vial. The way this works is that each of those small molecules is conjugated to a unique DNA barcode. And so a screening chemist would then immobilize their target to a bead, screen that library all together all at once, and then wash away the compounds that didn't bind. And so you'll notice this blue DNA code is conjugated to that red small molecule that was bound to the target. You can amplify that sequence and then sequence the DNA through next-gen sequencing, all to reveal the code that tells you what that original molecule was, or that small molecule was. It's a very quick process. And so typically this is done either through in-house DNA-encoded libraries, or the synthesis of these in-house DNA-encoded libraries, or through partnership with DNA-encoded library service providers. And so both of those have, very high barriers, costs to enter. And certainly with the service offer, there's, potential milestone payments down the road. And so where do we come in? And so the answer is in two ways. First is in synthesizing your own DNA-encoded libraries. And so we have a service called Aldrich Market Select, which has been used for years by screening chemists building their own libraries. And so it's a concierge service whereby you provide the information of what types of molecules you would like, in what format you would like them to be in, and then our team would collate that into basically a single product sent to you. And so no fuss, no muss. And so this is perfect for DNA-encoded libraries because, as you can imagine, there's certain types of molecules, fragments, or screening compounds that are most amenable to DNA-encoded library synthesis. So you would need, for instance, on each molecule, a chemical handle to conjugate to DNA. And so this is a way in which AMS can be used to help build those libraries. And in fact, the AMS group recently published in ECS MedChem Letters an article with Pfizer in which Pfizer has shown that this is a very effective way to make DNA-encoded libraries, and more price effective than the previous ways that they had done it as well. So obviously building DNA-encoded libraries isn't for everybody, and so what we wanted to do is to also be able to provide an off-the-shelf offering of DNA-encoded libraries. And so we have the market's first off-the-shelf DNA-encoded library. And so with that, you can purchase the kit. It comes with 5 different vials containing identical libraries, run 5 different assays, do your screening, amplify your DNA with PCR, do your next-gen sequencing, and then take that DNA code and then put it into our secure portal online, and it will reveal the top 20 hits for you for free. And so this is in contrast to subsequent libraries that have become available off the shelf, whereby you have to purchase the kit, but then you have to pay to reveal the structures afterwards. Okay, so great. So hopefully we found what we should make through lead discovery with these DELs off the shelf or through AMS. And now it's a question of, okay, well, how do I make this molecule? How do I make analogs of it? And so a question of reaction design. And so here's an example compound. So this is notabit C. And to most chemists, they would look at this and scratch out on a whiteboard how they might approach this retrosynthetically. And I think the only piece that's obvious is in that eastern fragment is the proline moiety. Other than that, it's anyone's guess how you'd like to approach this molecule. With Cynthia, you can put molecules like this in, program it to tell you the fastest, cheapest, shortest, greenest route, whatever, and then go from there. So for an example, notamid C placed into Cynthia in less than 5 minutes provided about 50 competent pathways retrosynthetically back to starting materials that are cheaper than peanuts, including proline, as you can see. So how does this work? And so importantly, and different from other retrosynthetic tools, the literature scraping aspect of these programs, or in Cynthia's case, is augmented with rules that were hand-coded by PhD organic chemists. And so tens of thousands of rules, in fact, were hand-coded. So what that means is that unlike in other processes or other software packages, stereochemistry can be considered. Reactions that weren't prevalent or found at all in the literature can be considered, etc. The other piece is that complements the hand-coded rules is the unique walking algorithm. And so there's an algorithm that walks back and forth along energetic pathways to find you that which is most chemically feasible. So of course, you're probably skeptical of whether or not this works, so too were we. And so the advantage of having various groups, synthetic groups within our company is we were able to put it to the test. And long story short, that you can read about in this cover article of Chem, peer-reviewed, was that in each case, whether a molecule that we were looking to make as an analytical standard, a bioactive small molecule, possibly for our pharma business, was either cost savings, steps reduction, able to bypass patents, etc. So it was universally successful in our hands, and that was the test that we needed to before we rolled it out to the market. So of course, now that you have a synthetic path, as I mentioned earlier, it's the hard part of actually making it. And so this this is the crux of most of the type of compounds that we bring in. We bring in about 300-ish products a year. Most of them are reagents, as you might imagine. And so they're in areas like cross-coupling, fluorination, CH functionalization, oligopeptide synthesis, and the like. So I would encourage you to visit sigmaaldrich.com/medicinal chemistry, or for what's new, sigmaaldrich.com/new chemistry, or talk to your local rep and or find on our site our user guides. This is something that we've come to find are very useful. And so we work with academics or pioneers in the field to write users guides for, in this case, CH functionalization, photoredox catalysis, cross-coupling, etc. Our synthesis enabling platforms are not traditional products. So these are either instruments or platforms that are useful in improving synthesis or improving synthetic conditions. And so catalysis is something that you may have heard of. And so what this is for a suite of pharma or drug discovery relevant synthetic reactions, including CN, CC, coupling, etc. It is a portfolio of pre-plated kits that have optimized catalysts, ligands, catalyst-ligand combinations for those reactions. It also comes with a starting kit, inertian box that replicates glove box conditions, obviously cheaper and more space effectively than a glove box. And so you can do these sometimes testy reactions on the bench top. And long story short, with a minimal amount of your precious substrate, you can quickly screen for what the best reaction condition would be instead of buying all the chemicals up front, all the catalysts, and using up a lot of your substrate. This too has worked in practice, and so both a borylation step and a cross-coupling step using this technology on 30 kilos was done in process by Merck Sharp and Dohn and published a couple of years ago. My favorite story of academic collaboration is certainly photocatalysis. And so a few years ago, we realized that a lot of synthetic chemists were buying what were photoredox catalysts, but they weren't buying them from us. They were buying them from our materials science division, our OLED division. And so we worked with Corey Stevenson, who's now at the University of Michigan, and he basically said, Ben, I'll tell you what dozen photoredox catalysts you need. If you send me all the starting materials, I'll make them all for you. Just let me keep half. And that kind of gave him years worth of supply of photocatalysts, and it gave us a good start. Of course, it's not just the catalysts, and of course now we've got dozens of them, whether they're iridium, ruthenium, organocatalysis, whatever. But as I mentioned earlier, the know-how, the knowledge gap of how to use this is being addressed by our user guide that was written in conjunction with the Macmillan and the Nischevitz group. The last issue with photocatalysis was, of course, instrumentation. It's very easy to do this. You can, Teshik Yun has classically done these reactions on the windowsill. So you can imagine that there's a lot of variance and poor reproducibility in this field. And so we've addressed this in three ways. So we have three photoreactors, one for screening. So it's an extension of our catalysis line. And so there's plates of photocatalysts that can be used with this bottom-lit photoreactor to screen for reaction conditions. We've got in conjunction with Synled and Dave Nashevitz, we've got this middle reaction optimization photoredox catalysis reactor. And then on the far right, for a larger batch scale up with variable wavelength, we've got the Penn PhD reactor that has been developed in conjunction with MSD, Merck & Co. and Princeton. And so those product numbers are below each column respectively. So lastly, into the space of, we've made these molecules, how can we use them more effectively? And so not every molecule is destined to be a blockbuster inhibitor. And so as I mentioned earlier, the chemical biology toolbox takes these small molecules, in this case, a bromodomain inhibitor, and uses synthetic chemistry tools to make them useful in biological systems. And so, for instance, turn it into a probe, possibly conjugate it to an antibody, or on the far right, turn it into a protein degrader. And so for our whole offering in this space, I would encourage you to check out sigmaaldrich.com/chemical biology. But I want to focus on this last piece, so this protein degrader. And so this is a topic that you may be familiar with, but in short, targeted protein degradation is a process that hijacks the cell's own protein degradation mechanism. And so typically, the cell will get rid of damaged proteins by approaching it in physical space within the cell with an E3 ligase, which tags it with ubiquitin. And so once tagged with that ubiquitin, that marks it for degradation by the proteasome within the cell. What a PROTAC is, and so a PROTAC is short form for proteolysis targeting chimera. That's a small molecule. It's a 3-piece small molecule that hijacks that same function, but instead of approaching a damaged protein, it approaches the protein of interest that is specific to that small molecule of your design. And so this is a new modality for drug discovery because it relies or it affects protein abundance rather than inhibition. So in that way, it's akin to or it's a small molecule analog to possibly to CRISPR or RNAi. And it's catalytic in PROTAC. It doesn't require or it works with low affinity target binding. And so it's really quite a nice new modality. The problem, of course, is in synthesizing these PROTACs. And so it's not just in synthesizing, and you can see it's a complex molecule here, but in knowing which ones to synthesize. So there's no empirical design yet. And so synthetic chemists or medicinal chemists are forced to, even once they have a small molecule selective for their protein of interest, they're then forced to synthesize libraries of these protein degraders. And so there's variability in the chain length, between the E3 ligase ligand and the protein of interest ligand. That chain can vary in length, solubility, rigidity, etc. You can choose different ligands for those different E3 ligases, and so there's all kinds of different variability. And so what we've been able to offer is what we call protein degrader building blocks. And so on this right-hand side, with variants in terminal chemistry, and so that are compatible to your reactive groups on your protein of interest ligand, different linkers, so variability in linker, so aliphatic, PEG, length, etc., mixed, and then variability in the E3 binder. And so with that, with one ligand, so one small molecule that's specific to your protein of interest, and together with our degrader building block library, of which we've commercialized hundreds, you can quickly synthetically make a PROTAC starting library to determine which particular PROTAC is that which degrades your your protein of interest. So just to summarize, I think we've kind of moved along that space from what to make, how to make it, making it, and then making it more useful biologically. This is a bit of a departure from our typical chemical synthesis remit. It's been a fun discussion. If you have any questions, please reach out to your account manager, or anything related to chemical synthesis innovation or potential collaboration. Please reach out to me at the address below. Thank you for your time.